11 kilometers per second. That is how fast a spacecraft hits Earth's atmosphere when returning from the moon. From the space station, it's 7.8, 42% faster. Sounds manageable, but kinetic energy scales with the square of velocity. That 42% faster means the heat shield must absorb nearly double the energy. This is the difference between coming home and not. And the engineering that makes that difference is what no one is talking about. To understand why coming back from the moon is so much harder than coming back from the space station, you need to understand one equation. Just one. Kinetic energy equals 1/2 times mass times velocity squared. That squared is everything. It means energy doesn't grow at the same rate as speed. It grows faster. A spacecraft returning from the space station re-enters at 7.8 kilometers per second. From the moon, 11.1. Plug those into the equation. 7.8 squared, 61. 11.1 squared, 123. That's a ratio of 2.03, 42% faster, double the energy. Think of it this way. A car crashes into a wall at 60 kilometers per hour. Now, the same car, same wall, 85 kilometers per hour. Only 42% faster. But the impact energy is double. The front of that car doesn't crumple a little more, it collapses. Same physics, same equation. When a spacecraft returns from the moon, the atmosphere doesn't warm the heat shield a little more. It goes from 1500 degrees Celsius to 2760, nearly the melting point of steel. Everything that follows, the materials, the angle, the trajectory, the silence, exists because of this number. Double the energy. That single fact reshapes the entire engineering, and the first thing it reshapes is the angle. Because that doubled energy doesn't just arrive, it arrives through a corridor that is exactly 1 degree wide. If you're the kind of viewer who needs to understand the why behind the engineering, not just the what, that's exactly what we do here on The Cosmic Rush. Hit subscribe, we're just getting started. When a spacecraft returns from the moon, it doesn't just fall into the atmosphere, it has to hit the atmosphere at a precise angle. Too shallow, and the atmosphere bends the trajectory upward. The capsule skips off like a stone across water and flies back out into space. No fuel to come back, gone. Too steep, and the capsule plunges into the dense lower atmosphere at full speed. The heat exceeds what the shield can handle. G-forces crush the crew. 12 Gs, maybe more. The capsule doesn't survive. The safe zone, the entry corridor, is plus or minus half a degree, 1 degree total. From low Earth orbit, that corridor is about 2 degrees wide. From the moon, it's cut in half the margin, double the energy. That's the trade. In April 1970, the crew of Apollo 13 lost most of their navigation systems after an oxygen tank exploded. They had to aim their reentry angle manually, using the sun through the window as a reference point. Half a degree off in either direction, and they die. They didn't miss. Today, navigation computers are far more precise than anything Apollo had. But here's what hasn't changed. The corridor is still 1 degree wide. Better computers help you aim better. They don't make the corridor wider. Physics doesn't negotiate. So you've aimed right. You're inside the corridor. The shield takes the hit. And the way it protects you is the opposite of what you'd expect. It doesn't resist the heat. It burns. On purpose. Most people assume a heat shield works by resisting heat, like armor. That's wrong. The shield protecting a spacecraft returning from the moon works by destroying itself. The process is called ablation. As the shield heats up, the outer material chars, melts, and vaporizes. Those gases carry the thermal energy away from the spacecraft, pulling the heat with them as they leave. Think of a pot of boiling water. The water boils at 100 degrees. As it evaporates, it carries heat away. The pot never gets hotter than 100. Ablation is the spacecraft version of that principle. Not all shields use this approach. The space shuttle used ceramic tiles. They insulated against heat and could be reused. Future concepts use ultra-high temperature ceramics that can withstand the heat without eroding at all. But for returning from the moon, right now, ablation is the only proven method. You burn the shield to save the crew. This is what that shield looks like inside. The outer layer? Char. Already burned. Porous. This is where the ablation gases escape. If this layer is open enough, the gas flows out. If it's not, below that, the pyrolysis zone. Material actively breaking down. Chemistry happening in real time at 2700 degrees. Deeper, virgin Avcoat. Untouched. A honeycomb structure filled with silica fibers and epoxy resin, waiting for its turn to burn. Then, titanium. The structural skeleton holding the shield together. And behind all of that, steel. And behind the steel, 4 human beings. In 2022, this shield flew on Artemis 1, the uncrewed test flight around the moon. When engineers examined it after splashdown, they found something wrong. Large chunks of the char layer had broken off during re-entry. The technical term is spalling, and the cause comes back to that porous char layer. Here's what happened. Artemis 1 used a skip re-entry. The capsule dipped into the atmosphere, bounced up, then dipped again. That first dip generated lower heat than expected. Lower heat meant the char layer didn't become porous enough. The ablation gases got trapped inside. Pressure built. And then, the char exploded outward. Chunks of protective material gone, at 25,000 miles per hour. NASA's fix was not a new shield, it was a different angle. For Artemis 2, they switched to a direct re-entry, straight in, no skip. Higher heat from the start means the char forms properly. Gas escapes, no spalling. But that fix has a cost. Direct re-entry means higher G-forces on the crew, 6 to 8 Gs instead of 4, heavier, harder, but survivable. The trade was more pain on the body, or a shield that might crack apart. NASA chose the pain. Now, a question you might be asking. SpaceX has its own heat shield material, Pika X, lighter, easier to manufacture. It flies on every Crew Dragon mission. So why doesn't NASA just use that? Because Crew Dragon returns from low Earth orbit, 7.8 kilometers per second. Pika X has never been tested at lunar velocity, 11.1. Avcoat has, on every Apollo mission, on Artemis 1. The physics is different at that speed, and the only material with flight heritage at lunar velocity is Avcoat, even with its flaws, even with the spalling, because in deep space engineering, a material that has flown and survived is worth more than a material that should work but never has. And then, after the shield has done its job, after the angle held, after the math checked out, comes the part no one can engineer away: silence. At 11 kilometers per second, the air around the capsule doesn't just heat up, it ionizes. The molecules lose their electrons. The gas becomes plasma, a superheated, electrically conductive envelope surrounding the spacecraft. And plasma blocks radio waves. All of them. For 3 to 4 minutes, mission control goes silent. No telemetry, no voice, no heartbeat data, nothing. The crew is alive, or they're not, and no one on Earth knows which. From low Earth orbit, that blackout lasts about 90 seconds. From the moon, 3 to 4 minutes, more than double. Because faster entry means thicker plasma. Thicker plasma means longer silence. And then the plasma fades. Signal returns. A voice on the radio. At 25,000 feet, 2 drogue parachutes deploy to stabilize. At 9,000 feet, 3 mains, each one 116 feet across. They slow the capsule from hundreds of miles per hour to 17. Splash. And it's over. Over 1,300 parachute tests across 20 years to make those 60 seconds work. Stack all 4 together. The math says double the energy. The corridor gives you 1 degree of margin. The shield burns itself alive to buy you 10 minutes. And then, silence. 3 minutes where physics holds your life and no one can step in. Every single one has to work. Not most of them, all of them. Every time. Now, you might say, Crew Dragon re-enters all the time. Astronauts come home from the space station regularly. What's the big deal? And that's true. At 7.8 kilometers per second, half the energy, twice the corridor, a third of the blackout. Lunar return is a fundamentally different problem. Same planet, different physics. And for context, Japan's Hayabusa missions return samples from asteroids at 12 kilometers per second, even faster than the moon, but with no crew. When there are people inside, every 1/10 of a degree matters. 42% faster, nearly double the energy, 1 degree of margin, a shield that protects you by destroying itself, and 3 minutes of absolute silence. Every spacecraft that returns from the moon must pass this exact test. Apollo passed it. Artemis is passing it right now. And whatever we build next, to Mars, to asteroids, to places we haven't named yet, the physics will be waiting. The same equation, the same corridor, the same silence. But the shield that passed this test was not built in America. The engine that carried the crew to the moon and back was built in Bremen, Germany, by the European Space Agency, and without it, nobody goes to the moon. That story is next. Subscribe to The Cosmic Rush.